The talk I'm giving now is about using one-sided MPI communication in order to improve the sparse triangular solve. And this is work together with Nandine, Sam Williams, Yang Liu. They are all at LBL, my colleagues. So sparse direct solvers has two main parts. One is the factorization, one is triangular solve. And factorization it can be very expensive for not only memory, but also computationally, it's quite a lot of work. And in most of the applications, large-scale applications, they don't do direct solver directly for the whole problem, so usually break into smaller problems. Canonical example is the block diagonal preconditioner. So there you have multiple blocks along the diagonal, and each block you do the direct factorization. And then the outside, you wrap this around, you use this as a preconditioner for GMRES, for example. And then the problem here is that you only need to factorize once of each block. And then you, every time in the GMRES iteration, you do the triangular solve many times. So that's the situation we're trying to deal with, is how to improve the triangular solve performance, even though by itself, it's not very expensive. Okay, so the particular algorithm I'm talking about today is in SuperLU library. And here the L matrix has supernodes in there. So you can think about all these non-zeros are blocks. And then I'm focusing on single right-hand side. If you do multiple right-hand side, you can be, the computational efficiency can be improved. And really the mathematical operation is here. You, for the previously computed component, you multiply them together with the off-diagonal block and subtract it from right-hand side. And then for the diagonal block, do a triangular solve. So the local solve is triangular solve, and local update is the MATVAC for this operation. And then the communication is a broadcast and reduce. So along the column dimension, you need to broadcast the X component computed. And then along the row dimension, you need to do the reduction to accumulate all these local sums. So as you recall from yesterday, Bob Lucas' talk, he was talking about all these sparse communication. This is actually sparse communication. It's not a broadcasting to everyone, okay? Okay, so the computation can be neatly represented as a DAG. So the computation is on each node is the local computation, and then we use level sets starting from the root here, the beginning here, and then you do the breadth first search to compute these level sets. That gives you all the dependencies, and also it tells you what's the parallelism within each level. So that's essentially what the computation graph looks like. And if you do this in the straightforward implementation in our earlier code, you can see that the communication actually dominates. So there's very little computation you need to worry about. So this is the 6 matrices selected from Sweet Sparse, and we run on the Intel KNL nodes. And here we have 1024 NPI ranks. And then that's the production code. In the earlier version, you will see this. So you can see that almost 90% of the time is in communication. And the volume of communication is small. It's a lot of small messages and just point to point. And then we look into the different MPI communication libraries. So the standard way to do communication is send and receive. So in fact, in our code, we use I send, I receive, So that helps a little bit overlapping of communication and computation. But then for the one-sided, what you can do is you can put directly into the destination. And then this is a MPI one-sided. It's a standard in the new, I think started MPI 4. And then another implementation, this is very well implemented in the on the Cray system from ETH. It's called a full MPI. It's not a full collection of the functions, but it has the critical ones. And the full MPI can be used together with the vendor existing MPI, so they don't conflict. So on the picture here is a micro benchmark about the bandwidth with respect to the message size. So you can see that one-sided communication using this full MPI library is, this green one is the MPI one-sided from the Cray implementation. It's actually not very good. And if you compare with the blue one, the two-sided, this Cray one is actually slower. The bandwidth is slower. But the good one is this full MPI gets a better bandwidth. And the difference, depending on your message size, it can be 8x difference or 3x difference. So that's the thing we're going to use. And then let's come back to the triangular solve. And in the SuperLU computation, we use the 2D block cyclic layout. So this is 9 processes arranged as 3x3 process grid. And each of the color here, the dot corresponds to one process. So there are a lot of 9 colors, and hopefully it's not too confusing. So what you do, the operation is you solve the root nodes, which are the free ones without dependency, and then you in-queue the new tasks using this MPI put. And then the receiver, every processor will dequeue a task using, there's a counter to know how many I have a task remaining to do. And then you just dequeue a task, then you either do the solve or either do the matchback depending on the message. So then after that, you will go back, you in-queue the new one and do the local computation. So let's take a look at these. So that's the beginning on the picture here. So let me move this. On the picture here, from left to right is the timeline, and this vertical is the 9 processes. So in the beginning, 0, 1, they are free, so you can ready to go. And then after that, so after that, process 0 can finish 4 and 5, one at a time. And then if you focus process 4, so 4 get X1 is computed, and then X1 will be communicated to process 7. It's needed for 2 here. It's process 7. So X1 is put in the process 7 queue. And then you continue, then 2 here will compute a local sum. It will be put in the queue of process 8. And at the same time, process 0 will compute it to X5, and this X5 is needed by process 6 at node 10. So we'll put X5, and here also put X5 into the processor 3, the queue. All this is managed by the queue. So that's the animation of this process for this small matrix. That's a timeline. So the implementation here is just to use 2 queues. One is the block column broadcast task queue. The other one is a block row reduction queue, which is accumulate all the sum. It's the reduction operation. So in this picture, it's a 3x3 process layout. And then we have 3 subcommunicators, a vertical subcommunicator and horizontal subcommunicator. So if you look at process 8, from this point of view, it will have the queue is divided by coming from different processes. It could come from process 2, or it could come from process 5. So 8 will not need anything from process 4. It's restricted within these process columns. So that's how the operation works in this setting up this task queue in one-sided communication. So essentially, if process 2 finished a task, if it's needed by 8, it will put the task into process 8, the queue, and this task could be either the it has the block column number and either the X components or it's the checksum. Okay, so let's take a look at the performance comparison of this one-sided versus two-sided. So here I have 6 matrices, but let's just focus on one of them. So let's say we focus on this ship sec1, this matrix. I don't remember the size of it. It's a relatively good size. And the process is coming, we run this on 3 process configuration from 256 to 4000. And this left, the larger bar is the worst one, is the older code using the two-sided communication. And this light blue one is the new one using the one-sided communication. So in this chart, you can see that that's the amount of communication time. And that's the local computation time. So the majority of the time in communication. So you can see that with the one-sided communication, what you reduce is really the communication time. The local time is the same. So essentially, we get across all these matrices, we get about a little over 2 times the speed up at 4,000 processes. So this is quite a significant for triangular solve to run on 4,000 MPI processes. So the next part, how much time do you have, Ian? So we get a good performance. Now the question is, where do we want to continue to optimize? What's the limit? So that's what we're trying to do using the performance model. Here what you need to do for the single right-hand side triangular solve, there's actually, you can consider computation. Floating point operation is free, there's nothing. It's mainly the data movement, which is on the local part for GEMB, or the communication for the remote part, which is the binary tree, either broadcast or reduction. So those are the 2 components we'll model. So our tool is to use the critical. Go ahead, Ian.
3 minutes.
3 minutes, okay. So the tool is to use critical path performance model. So in our code, currently we don't do clever scheduling. So all our algorithm following this level sets. So there's no clever scheduling. So if there's a parallelism across the 2 levels, we're not taking advantage of that. So then the critical path performance model, essentially you can just follow these levels. And for example, here. So the first step is simple. It's just you consider you have an infinite number of processes, and then you can just get the critical path along here, the longest path in this breadth-first tree. And the second step, you want to have a better refined model, which means that you only have 4 processes, for example, so limited resources. So that means within each node, within each level, you would want, if the 2 nodes, they are assigned to the same process, then these 2 things, they have to happen sequentially, one after another. So that's something we take into account. After this second process configuration, we will enlarge. In the critical path the length will be longer because of the sequentiality here. So that's the 2 steps. And then so this picture essentially is what I just said. So let's take a look at the local computation for dense MATLAB operation. As I said, there's no computation. It's really just the data movement. And the movement time you can measure as the block size divided by the bandwidth of the machine. So then we got the performance plot here. So the picture here right now, you have a perfect parallel. If everything is perfect, no communication, load balanced. And then we have a lower bound, which means that we don't worry about communication yet, but just to look at the heaviest load process. That's how much time you need to take. And then the upper bound is based on the critical path length and looking at all the local data movement, adding them together along the critical path. So you can see that there's a gap between lower bound and upper bound. And this is the observed on the critical path, observed computation. So the gap between the observed and lower bound is mainly because the task placement is probably not very good yet. There's room to improve in order to reach the lower bound. And then we are better than the upper bound. Okay, So basically, this performance model gives you some insights of the where you need to do the optimization for further improvement. And this model depends on matrix sparsity. It also depends on the matrix, how many processes you use, and the matrix decomposition. So the next is about the model, the communication, which is even more critical. And here we have two types of communication. One is broadcast, sparse broadcast. One is the sparse reduction. So the broadcast tree is actually latency. You only have one for each node, only one latency, and then the log 2 of the how many processes you want to fan out times the block size divided by the bandwidth. So that's summing up all together along the diagonal. That's the broadcast model. And the reduction model, it's slightly different because for reduction, you have to wait all the messages to come to the root. So that's why this latencies is actually has a factor of log 2 of the integrity. Okay. And then we do the last example is using this performance model to look at the communication of a dense matrix. It's very illustrative of this matrix. So the dense matrix is input as represented as a sparse matrix in the sparse code, and then we have a 1200 by 1200 size. So in this picture, there are several plots. The lower one, this dotted one, is the communication model, communication time actually, and the upper one is the total time. So as you can see, for dense matrix, communication time is not the whole lot because the off-diagonal block, you still have a lot of work. They are not on the critical path. They can happen simultaneously. So that's good. But one thing you want to pay attention is what's the best process configuration. Here we look at P by 1 by P, and square root process configuration. So it turns out for triangular solve, the P by 1 is actually the best in terms of communication. This is mainly because if it's P by 1, you do the vertically, is the you do the broadcast, but that doesn't, you don't pay too much cost of latency. But row dimension, you don't have any communication. So in that case, you save the latency for the row reduction case. So that's the final result.
We do have to stop, I'm afraid.
Yeah, so I will stop here. So this is just a dense matrix, the two different configuration, the critical path. You can see the critical path for this configuration is better than the critical path here.
Right.
So I will just put up the summary here. I can take questions now.
Yes, so thank you very much. We've got one question or comment really that's come in, and I have a question myself, and we've got time for that. Kumar was just mentioning, and I think you came to it just after his question came in, that latency is is a big issue for small messages, and more than the bandwidth even. And I think you were sort of addressing it. Combine that with a question I have, and you can do the double answer of these. Obviously, you've really got terribly small granularity. Now, if I told you had 100 right-hand sides all the time, then presumably you'll be able to get some better performances then somehow.
Yeah, so let me address the first question. The first question is about latency. That's a very good question. And that's why, from this model, you can see that the block row reduction is actually not good because we pay the latency cost of log 2 of these number of processes across row. And then if you do the block column broadcast, you only pay the latency of once, because then once this is done, this process can go off, do some other work. So that's why, your process configuration, it's actually not good to do 1 by P, because in that case, you will have more communication across the row. So that's essentially the same as the result here. P by 1 is better than 1 by P, because 1 by P you have row reduction.
Yeah.
So that's the first question. And the second question is small message about the right-hand side. So here we're trying to do the harder problem, which is a single right-hand side. So that's why in our local computation modeling, we are just modeling the GEMV, the matchback data movement. We are not modeling the flops because flops is essentially free in this case. And if you have 1,000 right-hand side, then you are doing local part is doing GMM, and then your model, we need to modify the model a little bit to basically take the maximum time of the data movement and the flops. If your GMM is pretty big, like in that case, you could have for maybe 100 by 1,000, then probably the flops will take over the data movement for the local part.